Traditional programming relies on humans writing explicit rules for every case. Machine learning, however, discovers patterns by analyzing many examples. What actually changes inside the system during training? The model adjusts its internal parameters based on feedback. This feedback comes from comparing predictions to correct answers. Let's start with the core ingredient, training data. It consists of input-output pairs, like images and their labels. Training data is labeled examples that teach the model. For a photo classifier, each image has a label like cat or dog. The label provides the correct answer the model should learn to produce. Without labels, the model would have no target to aim for. Quality and diversity of data are crucial for effective learning. Biased or small datasets can lead to poor performance later. Now, let's see how the model uses this data. Given a new input, the model makes a prediction. It computes an output based on its current internal parameters. These parameters start with random values. So, initial predictions are often far from the correct label. The model doesn't know anything yet, it's just guessing. But the guessing process is guided by the structure of the model. Each prediction is a step toward learning. After a prediction, the system compares it to the true label. This comparison produces a number called the loss. A low loss means the prediction was close. A high loss means a large error. The loss is the signal that drives improvement. It tells the model how wrong it is and in which direction to adjust. Different tasks use different loss functions. But the core idea remains the same: measure the mistake. Using the loss, the model adjusts its internal parameters. This is often done via a process called backpropagation. Parameters are changed in a direction that reduces the loss. Think of it as turning knobs to get a better output. Small changes are made iteratively over many examples. The mathematical details involve gradients and calculus. But the essential concept is repeated correction based on error. The cycle of predict, compare, adjust is repeated thousands of times. Each complete pass through the dataset is called an epoch. With each epoch, the model's parameters improve incrementally. The loss decreases as the model fits the training data. But training too long can lead to memorization. That's why we need to monitor performance on separate validation data. Repeated training refines the model's internal representations. The ultimate goal is not to memorize training examples. It's to generalize, perform well on new, unseen data. A model that memorizes but fails on new data is overfitting. Generalization requires the model to learn underlying patterns. Test data, not used during training, evaluates true performance. If the model does well on test data, it has generalized. This is the most important measure of success in machine learning. Training can fail if the data is biased, too small, or unrepresentative. The model may learn shortcuts that don't hold in the real world. For example, if all Apple photos have white backgrounds, the model learns background, not fruit. High training accuracy doesn't guarantee good performance on new data. Overfitting occurs when the model memorizes noise and details. Regularization techniques help prevent overfitting. The key is to ensure the training data mirrors real-world conditions. Machine learning is a process of repeated pattern adjustment from examples. The system learns by tuning parameters to reduce error. But the real question is, how well does it handle new inputs? Powerful as it is, machine learning is not automatically reliable. Its success depends on data quality, diversity, and careful training. Understanding these basics helps you evaluate AI systems critically. Thanks for watching. Stay tuned for more on data quality and neural networks.